If you get extra carry, then you have to ignore. If you're not getting any extra carry, then the result you have to converting into 2's complement and then you have to put negative sign. Computer codes helps us to represent the character coded from the memory of the computer. If I want to represent all the characters, it is not possible. Only 16 different characters we can able to represent. Welcome back to one and all. Myself, Vasanta, lecturer in computer science, Vidhyaashram, Pre-University College, Temple of Excellence, myself. Today we will start with the 6th session of data representation chapter. Whereas in the previous class, you come to know already regarding binary arithmetic, how to perform binary arithmetic operation, binary subtraction, how to perform binary subtraction, then representation of signed integer, that is sign and magnitude representation, 1's complement as well as 2's complement. With that, you have studied how to subtract a decimal number or a binary number using 1's complement. Whereas in today's class, you will come to know regarding 2's complement subtraction, how to perform 2's complement subtraction as well as computer codes under that BCD code, XS3 code, EBCDIC code as well as ASCII code. Now one by one we'll explain. First, if I want to perform subtraction using 2's complement, then some rules and regulations we have to follow. The first rule, find 2's complement of the subtrahend. That is, whatever value in the denominator we have, find the 2's complement. Whereas, in 1's complement subtraction, what we have done, we have find the 1's complement of the denominator value. Whereas, in the question if we get subtraction using 2's complement, then find the 2's complement of the denominator value. Then add with the minuend. Whatever result we get from the 2's complement, add with the numerator, that is minuend. If there is carry generate, then carry is called as end around carry and ignore that carry if it is generate. If I get carry 1, ignore that carry. If there is no carry, generated, then recomplement and put negative sign to get the final result. Recomplement means the denominator value or whatever result we get, that we have to converting into 2's complement and you have to put negative sign to get the final result. Now we'll explain with some problems. Consider we have subtract 14 from 25 using 2's complement. Whereas in the previous class you have come to know by using 1's complement how to subtract. Whereas in today's class you will come to know how to subtract a number by using 2's complement subtraction. First thing you have to identify which is the numerator and which is the denominator. If you observe 14 from 25, then here from word you have, it means that the numerator will be, that is minuend will be 25. Numerator represents 25. From here 14 from 25, then denominator represents 14. Numerator can be called as minuend and denominator can be called as subtrahend. And then find the equivalent binary number for both the numbers. For 25, find the binary values. For 25, the binary value is here 2 1s are 2 2s are, that is 12s are, remainder 1. Then 2 6s are 12, remainder is 0. Then 2 3s are 6, remainder is 0. 2 1s are, remainder 1. Then in the same way, find the binary value for 14 also. Then 2 7s are 14, remainder 0. 2 3s are 6, remainder is 1. Then 2 1s are, remainder is 1 here. If you observe here, 1, 2, 3, 4, 5 bits here we have, whereas here 1, 2, 3, 4 bits we have. Then write in the equivalent binary number. First you have to write from bottom to upward direction. Then here we are getting 1 1. Then here 0 1. 0 1. For 14 also we have 111 and then 0. But here we have 5 bits. That's why here 111 and then 0 we will write. See here, from bottom to upward direction we will write the value. then 111, to make equivalent, write down 0 here. Keep the numerator as it is, don't make any change in the numerator value, keep as it is, but convert the denominator value to 2's complement. How to convert this into 2's complement? Take down the binary value as it is here, 0, 111, 0 we have. First find the 1's complement of that number, then the value represents 1, 0001. Then add 1 to that. Then 1 plus 1, 0 with carry 1, 001. Now write on that value, that is 1, 001, 1, then 0. Then add both the values. Here 1 plus 0 is 1, 1, 0, 1. Here 0 with carry 1. If I get extra carry, then what is the procedure? If there is carry generated, then discard that carry, ignore that carry. Here I get one extra carry, ignore that carry, and the final result, this is the final result, that is 0, 1, 0, 1, 1. If I get extra carry, you have to ignore the carry to get the final result. If there is no carry generated, on that case, you have to convert this result to 2's complement and then you have to put negative sign to get the final result. Consider one more problem. Consider here you have subtract 35 from 18 using 2's complement. Then how to find? First, from this you can observe the numerator represents the 18 and the denominator represents 35. Find their binary value for both the numbers. For 18, the binary value you have to find out as well as for 35. 2 9s are 18, remainder is 0. Here 2 4s are 8, remainder is 1. 2 2s are remainder is 0. 2 1s are remainder is 0 here. Then for 18 we have find out. Next for 35 also you have to find the binary value. For 35 also here 2 1s are 7s are remainder is 1. Then we have to divide this 17 by 2s are, then 2 6 are 12, 7s are 14, 8s are there it will be 16. Then 8s are 16, remainder 1, 2 4s are 8, remainder is 0, 2 2s are 4, remainder is here 0. Once again 2 1s are remainder is 0. If you observe here 1, 2, 3, 4, 5 bits here we have. But here 1, 2, 3, 4, 5, 6 bits. Then how to write their binary value? Now write on their binary value. For 18, write down 1 0 0, 1 0 0. Then afterwards 1 0, then 1 0. Now in the same way for 13 also, for 35 also write down 1 0 0, 1 0 0. Then afterwards here from bottom to upward direction you have to write 1 0 0, then 1 1 you have to write. To make equalize here you have to write 0. Keep the numerator as it is 0 1 0 0 1 0 and convert the denominator value to 2's complement. Then how to convert this denominator value 1 0 0 1 1. Then first convert that into 1's complement. Then 1 on the place of 1 0 0 1 1 0. Then add 1 to that to get the 2's complement 1 0 1 1 0. Now write down that value 0 1 1 0 1. Now add these two values. Here 0 plus 1 is 1. Here once again 1 plus 0 1 1 1. Here we have 1 plus 1 0 with carry 1. But here we are not get any extra carry. If you observe the previous problem here, if you get extra carry, then you have to ignore. If you are not getting any extra carry, then the result you have to converting into 2's complement and then you have to put negative sign. See, first I will find the 1's complement, then here 0, 0, 0, 0, then 1, 0. Just replace all 1 by 0 and all 0 by 1. Then next add 1 to that. Then 1, 0, 0, 0, 1, 0 and with that you have to put negative sign to get the final result. See here minus 0, 1, 0, 0, 1 is the result. It means that if you get extra carry in 2's complement, then you have to ignore. If you're not getting any extra carry, then whatever result we get, convert that into 2's complement and you have to put negative sign to get or to subtract a given number by using 2's complement. Now is it clear for all of you? Next we will explain regarding computer codes. What do you mean by this computer codes? When you come on number system, already I told you there are 4 types. One is under positional as well as non-positional. There are 2 types, positional and one more is non-positional. But when you come on positional, 4 types. One is decimal, binary, octal as well as hexadecimal. Now whereas under this, computer codes helps us to represent the character coded from the memory of the computer. These codes represent specific format which are used to record data. There are commonly used computer codes are binary coded decimal number system, extended binary coded decimal interchange, then American Standard Code for Information Interchange, that is ASCII, then XS3. There are 4 types under computer codes. One is BCD, EBCDIC, ASCII as well as XS3. Now one by one we'll explain. First we'll explain regarding BCD code. The BCD code stands for binary coded decimal. Binary coded decimal. It is one of the early computer codes. In this coding system, the bits are given from left to right. The weight represents 8421 respectively. Then the BCD code equivalent, each digit is shown in the table. See here, if you observe here, consider the digit 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. That means to represent each character, we have to represent 4 bits. 0 represents 4 times 0, 1 represents 0001, 2 represents 0010, for 3 represents 0011, for 4, 0, 1, 00. In the same way, for 5, 0, 1, 0, 1, for 6, 0, 1, 1, 0, for 7, 0, 1, 1, for 8, 1, 4, 3, 0, for 9, 1, 0, 1. It means that maximum I can able to represent only 4 bits. That is not sufficient to represent all type of numbers as well as characters, is it? No. Whereas in BCD, if I want to convert any number to BCD, see, for their each and every number, you have to write their 4 equivalent bit number. For 5, see here, if you observe 0, 1, 0, 1. Here for 5, 0, 1, 0, 1. For 3, 0, 1, 1, 0. For 7, 0, 1, 1. Hence the BCD number code for 537 is 1, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1. This is the BCD number for the given decimal number. In 4 BCD, when 2 to the power of 4, that is 16 configurations are possible, which is insufficient to represent the various characters. It means that here, if I want to represent all the characters, it is not possible. Only 16 different characters we can able to represent. Hence, 6-bit BCD code was developed by adding 2 zone position with which possible to represent 2 to the power of 6. That is 64 different characters can be represented here. Whereas in the beginning, only 16 characters they can able to represent. Later on, by adding 2 bits, they can able to represent totally 64 bits. Next, we will explain regarding the XS3 BCD code. XS3, what do you mean by this XS3? Whatever digit we have, whatever numbers we have, by adding by 3, we can able to access the code value. The XS3 BCD code is non-weighted code used to express decimal numbers. Whichever number you want, that number we can able to represent by using BCD code. The name XS3 code is derived from the fact that each binary code is the corresponding BCD code pulls by 0, 1, 1. That is, by adding 3 for each and every digit, we can able to get the value here. This code is used some old computers The following, especially here I am going to show you the table. There the table represents the XS3. For example, 0. The BCD code is 4 times 0 we have to write. But when you adding 3 to BCD, then here we have to add another 3 here. Then 00 here we are getting, that is 0011. That means we are adding by 3 here. Then 1 can be represented here 0, 1, 00. 2 can be represented as 0, 1, 0, 1. 4 can be represented as 0, 111. 5 can be represented as 1, 3 times 0. 6 can be represented as 1001. In the same way, 7 can be represented as 1010. 8 can be represented as 1011. And 9 can be represented as 1100. It means that each and every bit are accessed by 3 here. That I will show with some example problems. Consider we have 537. It's a decimal number. First, I will write their binary numbers. That is 0, 1, 0, 1. For 3, 0011. For 7, 0, 111. Then, when you add with the 3, for each and every digit, separately we have to add 3 bit, 3 extra digits we have to add. Then here when I am to add 0011, here 1 plus 1 is 0 with carry 1, then 0 with carry 1, 0, 1. This is the XS3. Then here for 3, once again we will add by 3, then 0, 1, 1, 0. This is the, when you access the 3 value, then it will access it by 0, 1, 1, 0. Then for 7 also, we will add 3. Then 0, 1, 0, 1. It means that each and every digit we can able to access by 3. 3 see here, for 3, 00, 11 represents 3. Then if I have 5, then for that also we will add by 3. Then that represents 8 here. Now is it clear? Like this, we can able to perform XS3. And the next one, EBCDIC. EBCDIC. That it stands for Extended Binary Coded Decimal Interchange Code. Usually you will get the expansion of this. That is Extended Binary Coded Decimal Interchange Code. It is developed by IBM. It uses 8-bit code and hence it is possible to represent 256 different characters can be represented. Bit combination. Each EBCDIC is used on most computers, and computers are mainly nowadays are using this EBCDIC code. It is coding method generally used by larger computers like mainframe computers to represent letters, numbers or other symbols in the binary language. And the computer can use this type of EBCDIC code. EBCDIC code contains 8 bits to represent each and every characters. Whereas the next one is ASCII. ASCII stands for American Standard Code for Information Interchange. Whereas here it mainly uses 7-bit code in the beginning, which is possible to represent only 128 different characters can be represented. And it is used most in microcomputers and mini computers as well as in mainframe computers. They are using this. Then later on, this is dividing into ASCII 8 and then ASCII 7. Whereas in ASCII 7, they can able to represent 2 to the power of 7 number of characters, different characters they can able to represent. Whereas in ASCII 8, 2 to the power of 8 different characters can be able to represent here. ASCII 7 is 7-bit code for representing English characters as numbers with each letters assigned a number from 0 to 127. Different characters can be represented here. This completes your data representation chapter. Next class, we will meet you once again with a new chapter. Thank you for all of you.